Okay, in this video we're going to talk in a little bit more detail about something we briefly touched on in the last video. This is addition across an alkene of a small molecules such as bromine or chlorine. Okay, so you're going to see that at least initially this mechanism is very similar to the addition of, say, HBr across an alkene. It occurs with exactly the same first step. The difference then becomes because you have a bromine connected to a carbon and a bromine next to a carbocation, that something else is going to happen which will determine the fact we have two different products here. Don't worry right now about the relationship between these two products. That's a stereochemistry issue that we haven't got to yet, and we won't. I just want to make sure you understand there are going to be two different products here. And I also want to make sure you guys can understand that these dots here are supposed to represent a dash. Sometimes pain in the ass software here doesn't allow me to do this without joining the two lines together, which is very annoying. So what I'm going to try and do here is go through the mechanism to illustrate to you exactly why these two products are being formed. And this anti term here, all this means, anti means the two groups added on in opposite directions. So if this bromine points up, that bromine points down. So if you will, they're kind of trans to each other, but it's not really trans because we're not talking about an alkene. But they're pointing in opposite directions. It's sort of like one is on one carbon pointing up, one is on the other carbon pointing down. So you've got one bromine here and one bromine here. So they're anti to each other. That's what anti means. Okay. So the reaction starts off in exactly the same way as you've seen before. A pair of electrons come out from the pi bond, and you're probably thinking, well, there's no electronegativity difference here, so what's going on? Well, bromine is big enough, it's big enough of an atom that if you bring this lone pair over to here, you'll be able to push some of the electrons in this bromine and in this bond away from these incoming electrons, push them over onto this side, and thus induce a small positive charge on this bromine and a small negative charge on this one, allowing for this to become electrophilic, which then, because you know bromine can only form one bond, it causes that bond to break. So what you've got here is nothing different to what you've seen before, except that you're adding bromine rather than hydrogen. Okay, so if I just say, okay, well, my bromine has added on to one of these carbons in the double bond, and let's just say I'm going to add it onto this carbon, and I'm going to have it adding in from the top. The alkene here is sp2 hybridized, it's flat, so the bromine could add in either from the top or the bottom, so I'm just going to say it adds in from the top. So I'm going to show it on a wedge. So all we've shown is that the bromine adds to one carbon, at least so far. And if that's the case, I've got to have a plus charge on the other carbon, just like we do normally. Now, because of that, the bromine actually has three pairs of electrons here. And what do you think that bromine is going to do, given that it's got all these electrons and it's right next to a plus charge? Well, this carbocation is saying, give me some electrons. So that's what this guy does. It gives it some electrons. And what it forms is something called an intermediate bromonium ion. Let me just draw this structure out. Now, bromonium means it's essentially a three-membered ring, so let me try and draw this out. This bond here is a wedge, because the bond here initially was also a wedge. If this bond here was originally pointing up, then the bond here has got to be pointing up too. It's physically possible to bind one atom with one bond pointing up and one bond pointing down. You'll find this if you try and make a model of this with one bond up and one bond down. It's physically not possible. Now, there was a plus charge here, everything else was neutral, so where would the plus charge be in this case? Well, the plus charge is actually on the bromine, because bromine's now got one too many bonds. This is what we said was the bromonium ion. And I can't spell it, bromonium ion. And so what we have then is a situation that we also have our bromide ion that we removed in that first step, which is now going to come in. And the thing is, we can do this possibly two different ways. Now, you could argue that this bromine is going to attack either this carbon here or this carbon here, because both of these already have 4 bonds and can break a carbon-bromine bond to add in another one. You could argue that this carbon is slightly more hindered by steric hindrance because there's more alkyl groups coming off this carbon than this one. But the fact is you'll form a mixture of both products regardless of the percentage composition. So let's see what we can do. Let's see if we can figure out something. And it's important for us to understand that if this bromonium ion, if the bromine is sticking right up, just imagine again the rest of the molecule is essentially flat, and sitting up above it like a hat is the positively charged bromine. Now if that's the case, where is this other bromine going to come in from? Just imagine the other big bromine's up on top, so this one is going to have to come in from the side, the only side it can access the molecule, which is the bottom. So depending on what it's feeling like, it's going to attack either this carbon or this one. So let's say it's going to attack this carbon. Alright? If that bromine attacks that carbon, carbon, as we know, can only form 4 bonds, so that bond is going to break. And what we've done is, if I just draw out the carbon skeleton again, what I've done is I've added another bromine onto this carbon, but it came in from the bottom. So for that reason I'm going to show it on a wedge. Again, this is my crappy representation of a wedge, and that should be blue, shouldn't it? Bollocks, let me try it again. So if this is in blue, there's my BR on the dash. Now if that was the case, this other bromine, this carbon-bromine bond broke, but this one didn't. And if that was on a wedge before, it's still going to be on a wedge now. So I'm going to show it like so. So what I have here is my 2 bromines, one on a dash, one on a wedge, one pointing up, one pointing down, essentially the same as this guy. So these two are anti to each other. Now can you guys figure out where this one would come from? Well, simply it would come from if this bromonium ion had attacked here. Now, here's one thing for us to make sure that we are very clear on. Alright? If a question asks you to provide a mechanism for the formation of both of these two, the one thing I absolutely, and I mean abso-bloody-lutely, if you're asked to draw a mechanism of these two, the thing I do not want is for you to draw this. And you say, well, that's fine, that's what's happening in both cases. But the problem is what you're showing here is that this bromine is doing 2 things at once, which obviously we have touched on before you can't do. So if you're going to draw out these 2 separate mechanisms, or this reaction happening two different ways, what I plead with you to do for the sake of your grades is to make sure that you draw this reaction out, or this step out, twice. First you show the bromide attacking here to give this product, and then you show the bromide attacking here to give this product. Alright? And that is anti-addition of bromine across a double bond through the cyclic bromonium ion. This also works for chlorine too.